think about a couple of, I know this feels like a bit of a overload on tech, but I just want to highlight a few things because you're going to see them come up in the lesson today. So when we study probability, we need to be able to use these things called Venn diagrams to help us solve probability problems. And we need to be able to correctly identify the following things. So the sample space of an experiment. So I was calling that the set S last week. The idea that the sample space S can have events within it. And often we will call those events like another letter, like A or B or C or whatever letter we like. We talk about it being possible to have two events at the same time, which we call the intersection, or the intersection of two events. We would often use the word and. The way that would look like on a Venn diagram is if this whole thing was the sample space and this was A and B, then if something happened that was in A and B, it would be this area here. And we call that the intersection of the two sets, which is over here. Whereas the union of two sets is literally like basically everything within those two sets. And that is kind of related to the word or. So that's the or, and this is the and. So I just want to ask, does everybody understand the and or idea? If not, now is a good time to ask a question. Give me a thumbs up if you understand the idea of like something happening which is in two events. It's and, or the intersection, and it being in either of the two as or. So I just want a quick vote. Thumbs up if you understand this idea, thumbs down if you don't. Okay. Then when we deal with Venn diagrams, there is an identity that basically everything in the sample space, all the events together have a probability of 1. So basically what that means is that there's a probability that one of the events in the sample space will happen. And then you will also see this identity. It's called the additive identity. And I'll point this out as it goes today, but it's basically saying the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And so that is something which I'll explain more in a question, but just to point it out, if the events are mutually exclusive, now what mutually exclusive events look like is they have an empty intersection. So it's not possible to be in the event A and the event B. The moment you're in this one, you can't also be in this one. And these events, if A and B are in that format, then because their intersection is empty, because A and B is just 0, essentially we can just say that is true. And then the last identity that comes up is something called complementary events. And complementary events basically, essentially, they look like this in a Venn diagram. So if we had the one side as A, the other side would be A dash. So they're mutually exclusive. So once you're in the one event, you can't be in the other, but you also fill the whole sample space. So if this one was going to be, say, 0.6 probability, this one would have to be 0.4. The main thing I just want to point out are the words. So the main thing I want you to take away from this early part is the words and or when dealing with sets, the idea of complementary events, mutually exclusive events, and then these identities. And you're going to see them come up during the lesson today. Before I move on, are there any questions? That was a very quick little overview, that they will seem easier when we actually do the questions. But are there any comments or questions from the students before we get going? Okay. Anything? Okay, let's move on then. Let's start with a simple Venn diagram question. So you are given the following situation. It says there are a group of 27 girls, 10 play netball, and the rest do not play netball. And then it says, I want you to answer the following questions for me. I want you to do A, I want you to do B, and I want you to do C. Actually, I want you to do these four, A, B, C, D. And I'm going to give you some time to do that. And then once you've done that, I'm going to come along and draw the Venn diagram. And then we'll talk about question E. Okay, off we go. If you are stuck, feel free to raise your hand and we can have a chat. But for most of us, I think, well, yeah, let me know if you're stuck, but I want all of us to try and do A, B, C, D by thinking about what we learned in the previous lesson. And if you like, if you have the time, you can always put your answer for A in the chat if you feel confident. B is hard to put in the chat because it's a diagram, but C and D you can also put in the chat. Okay, so I see lots of people are saying 17, and I agree the answer for A is 17. Because if you've got a total of 27 and 10 play netball and the rest do not, basically you just go 27 minus 10. You get 17. Yeah. So the way I would draw this Venn diagram is I would just do this, and I would say this would be the ones that play netball, and then outside of that, in the sample space S, these would be the ones that don't play netball. And when you do Venn diagrams, you can either put the probabilities or you can put the numbers. In this question, I think the numbers would be easier. So I'm just going to put a 10 here and a 17 there. However, it's not wrong. You could also put the probabilities. It just depends on the question. Okay, so that was my Venn diagram. What about C? Are the events play netball and do not play netball complementary? Yes or no? How do we know if two events are complementary? Well, they're mutually exclusive, so they don't overlap, and they fill the whole sample space. And so in this situation, can you see that you can't play netball and also not play netball? Basically, these are two separate worlds, and there are only two types. They fill the whole sample space, so they are complementary. Yes. The other thing you'll see about complementary events is that they follow that probability PA equals 1 minus PA dash. And we'll get to that in a moment. I'll show you that. Yeah. Lasanda, what is your question?
Hello, sir.
Hey.
So I wanted to know how do you find if they're complementary?
Okay. So there's two things that for them to be complementary. The one is that they can't overlap. They have to have what's called an empty intersection. And then the other thing is they need to fill the whole sample space. So if you play netball, you can't also not play netball. Does that make sense, Lusanda?
Yes.
And then the other thing is, in total in this group, there's 27 girls. The people who don't play and the people who do together add up to 27. So they fill the whole sample space.
Okay, thank you, sir.
Yeah. Okay. Now, if you look at D, N of S, what is N of S, guys and girls? What's the number of items in the sample space? Yeah, it's the total number of items in this thing, and it's 27. So the answer here will be 27. Okay, then here's the probability question. Of the 27 girls, one of the 27 girls is chosen at random. Determine the probability as a common fraction that the chosen girl plays netball. So what is the answer to that going to be? What is the probability? We would say it like this: if N is netball, what is the probability that the random person chosen from the group plays netball? And you can put it as a common fraction. It's just going to be, well, how many possible outcomes are there? There's 27. How many of them are favorable for playing netball? They are 10. So the probability is 10 over 27. What is the probability? So that's the first one, 10 out of 27. What is the probability that the person doesn't play netball? And I'm using the notation N dash to say doesn't play netball. That means the complementary, the one that's, it's the not N. What's that going to be? So now we're looking at this area out here. And so this is going to be 17 over 27. Yeah, piece of cake. And just to show you that if you look at these two probabilities, right? If you take the probability of N dash plus the probability of N, what do you get? So what do you get if you add the probability of N dash but plus the probability of N, where N is playing netball and not playing netball? Okay, you get 1. Yes. And so this is the other way you know if two events are complementary. If their probability, when you add them together, if their probability adds to 1, they would be complementary. Okay, and if you rearrange this, like you can rewrite it as P of N equals 1 minus Pn dash, but that you don't have to do it like that. It's just to point out. So this is that complementary relationship that we were talking about earlier. Okay, give me a thumbs up if you feel okay. Give me a thumbs down if you like, slow down, Mr. Math teacher. Okay, then I think if my people are happy, then I shall move to the second thing. But please ask your questions. We are here to try and get you on the road. Okay. Let's try a second.
Mr.
Yes.
Police was asking if you could please explain again.
Which part, Liswa? Is there any particular? Because what I'm going to say is, for now, I think just maybe give a very specific part of it. I'll go over that in the next example. Okay.
Could you please explain the last part of
the last part?
Yes.
You're talking about this bit here?
Yes.
Okay. So basically, all I wanted to show you is that these two events, playing netball and not playing netball, are complementary events. And when events are complementary, the probability of those two, like if you add the probability of an event and the probability of its complement, it will always add to 1. That's all I wanted to show you. So it was more just like I was saying it. Okay. let's have a look at this next one, and then let's do this one. Let's try and do example 9 here, and then see if some of these ideas come through. The same idea will clarify. So I'm giving you a Venn diagram over here. A survey of 100 learners shows the following. 69 learners have an older sibling, 41 learners have a younger sibling, and 25 learners have both. A sibling is a brother or sister. So if you're an only child, you wouldn't have any brothers or any siblings. Okay, I want you, everyone, to try and do for me A and B. So the whole of B here. Try and do these ones. But I encourage you, as you do them, if you're stuck now, as a Zoliswa, if you want to ask about this, I would encourage you to do so now during the question, and we can talk about it. And then as you, I'd love to see the answers for A and then BI and all those things as you go. Let's do this. So how many, you know that there were 100 students who were surveyed, which we would call the sample space. And how can we, what regions are maybe missing here? How many learners have no siblings? Yeah, Awami, let's go to you. Hi, Awami.
Hello, sir.
How's it
I
going?
was gonna ask the sample space, like when you add up all of the figures given to us, it's higher than the sample space. Is that normal?
Oh, that's a good question. Well, let's see. So are you saying 44 plus 25 plus 16? I get 85, Awami. Do you get
16? Isn't it 69 plus 41 plus 25? So
so if we, this is really important. So, and I love your question, Awami. It says 69 learners have an older sibling. And what we notice is that the older sibling circle has 44 plus 25, which does give 69. But there are 25 students who have both an older sibling and a younger sibling. And we call, so they're they're in the and part or the intersection. And so it's a bit sneaky like that.
okay, thank you, sir.
Perfect. And so what we should be saying is the size of the sample space, N of S, is 100 because of this 100 here. And so in order to find out what this region is out here in the Venn diagram, we need to actually go 100 minus 44 minus 25 minus 16. 100. And I get 15, which means there are 15 students who have basically 15 only children. Does that make sense? Like people who don't have older siblings or younger siblings. So if we think about the Venn diagram, the reason it's so helpful is it allows us to visualize the different combinations that are possible in the question. Now we want to ask ourselves, what is the probability of, it says here that a learner chosen at random has an older sibling. So I'm going to say, what is the probability of O, where O is the older sibling? Now, to highlight which Venn diagram I'm very interested in here is, it feels for me that's the O, but now what is the probability if I choose a random person from the survey that they have an older sibling? So how many possible outcomes? It feels to me like it's still 100 because there are 100 people that I'm choosing from. Like I'm putting my hand in the jar and there's 100 choices. So that's fine. what is favorable for my question? An older sibling, well, in the group, there are 69 people who have an older sibling. And so it would be 69 over 100 or 0.69 or 69% chance. So it's quite likely that you'll choose someone who has an older sibling. Okay, so that one over there is done. What about the probability of having a younger sibling? What's that going to be? I'll look at the chat. I don't want to steal your thunder. Okay, so it feels like the 100 stays the same, but now the event I'm looking at in the Venn diagram is this one, which is 41 out of 100 or 0.41 or 41%. What is the probability I have an older and younger sibling? So what we would call what's the probability I have an older and a younger sibling? So remember, the key word is and. What does and mean in probability? It means it's both. You must be in the Venn diagram where you can fall in both circles. So an older and a younger sibling. What region am I going to be looking at? So if you have an older and a younger sibling, it means you have to have both. And the only people who have both older and younger siblings are the ones in the intersection of the two sets, or the green region I'm drawing now. So what is the probability of having, the way I would say it is O, older and younger. Or we could say it like this, O and Y, but that looks a bit, a bit scary, like an unhappy face, but that's what it's asking. So it's going to be 25 over 100 or 0.25. What is the probability of having no siblings? Last one. Okay, and the last one, let's do it here, is just going to be, so I'm going to say not, okay, I won't do the fancy, I'll just say, just say P for now, I'm not going to use fancy notation. It's just going to be 15 over 100. Okay, now that wasn't too bad. All I want to do now, are there any questions or, so Kumutsile has asked, so if you have a smiley face facing upwards, what does that mean? Okay, let me show you Kumutsile in the context of this example. If I said to you, they haven't asked this question, but if I said to you, I'm going to make up on the spot, what is the probability of having an older or younger sibling? If I wrote that, so older or younger, what is the probability of having an older or younger sibling? I could write that as O or Y. It basically means it could be an either. It's what we call the union. Can you guys calculate the probability of someone having either an older or younger or both for me? So the smiley face basically is telling you this is the region. It could be on this side, or it could be in this circle here. We call that the union. So I'll wait for some answers now. So the number of possibilities is still 100, but actually I need to add up all these things. So 44 plus 25 plus 16. So it's 85 over 100, 0.85. Okay, awesome. Now, there's not going to be time for us to do C, so I'm going to do that. But basically, if you want to draw a Venn diagram, instead of drawing it in terms of numbers in the set, you can also draw a Venn diagram with probabilities. And so just to show you what that would look like, because you guys have already worked that out, over here, it would be 0.15 because it was 15 over 100. Over here, it would be 0.16. Here, it would be 0.25. Here, it would be 0.44. And all I did to get the probabilities was I took the number of items in the set, so the n of whatever thing I was looking for, over the n of S, where S was the sample space. Now, what do you notice? What do you notice about all of these probabilities together? We're going to have a break in a moment, but I just want you to take a moment. If you look at all these probabilities for the different regions and you add them, what do you get? Okay. So the probability, if you add them all up, is going to be 1 or 100%, because there's 100% chance you will get one of these types of students in your group. Okay. The other, when you add probabilities, it will always add to 1 because it must be one of the possibilities in the end. Okay. Then the other thing, okay, we'll go back to that later stage. I tell you what, it's time for a break. So what I want is I want everyone on their feet and I want their cameras on and I want you standing up and stretching because we have done some hard work and our brains need a break.
Come on, guys, please join us in this
Pop those
stretch.
cameras on, everyone. Show me your lovely faces. I want to see you smiling.
We'd love to see your
Let's do this
faces.
together. And just
Shout out to
stretch.
Nolwazi, Lusanda, Rosette,
Oh,
William. Yes, guys, give your mind a
believe me.
break.
Show probability who's the boss.
Yes.
You are.
Shout
You
out
the
to Elise. There we go.
Oh, the
Shout
stretching
out
is bringing so much happiness.
Nobisutu.
There we go. Oh, make sure you hear things clicking, but not your
Yeah.
mouse. Okay. Oh,
Oh yeah,
okay.
definitely got to click.
There we go. And shake it out, guys. Shake it out like it's. Oh, I'm loving my students right now. I'm seeing such wonderful energy.
Loving this energy, guys.
Okay. All right. Time for us to show probability who's boss again. But before that, we must have a brain break. So this is your brain break for today. I want to know what you think about this. So you're given 3 positive numbers. You can add these numbers and multiply them together. The result you will get will be the same. Which are the numbers? Oh, you guys are a smart bunch. Ish. Okay, so you're quite right. The answer is, and I think, let's see who was first here. Yeah. Well done. Okay, lots of you. Okay, well done. Lots of people have got it. Hariva, I see you were quick on the draw. So 1 plus 2 plus 3 is 6, and 1 times 2 times 3 is 6. And so the answer should be 1, 2, 3. Simple
Great
as
going, guys.
well done. They were quick.
Yeah,
Okay.
very.
Let us, should we do that one? Okay, now let's do this one. Let me put that away for a moment. Okay, so here is the question. Let's do this. So find the probability that a boy chosen at random, I cut the rest of the question off. I'm going to say plays cricket. Find the probability that a boy chosen at random plays cricket. But I also want you to draw the Venn diagram because I'm going to ask other questions in a moment. So put this information into a Venn diagram, put the intersection in first, and then find the probability that someone chosen at random plays cricket, and then find the probability that someone chosen at random does not play cricket. Let's try and do that. And then let's say plays cricket or rugby. I'm just generating these questions here. Okay, let's try and do that. So we normally draw the sample space as a rectangle. And the important thing is the two events. There are some people who play both. And because we know there's someone who plays both, we call that the intersection of the two events, the and. And so we know my circle is going to have an overlap because of the fact that there are people who play both. That's quite important because it doesn't have to have two circles like the last one. This one does, though. So first question, what's the probability that a randomly chosen person plays cricket? But in order to do that, you're going to have to fill out your Venn diagram first. It says start with the intersection, which is 70. So 70 people play rugby and cricket. I want to know from the audience, audience is not the right word, for my students, how do we work out this zone over here, given that I've got 70 here and I've got 160 here? Oh, yeah. Who would like to tell me, raise your hand and tell me how I get to the promised land there? Okay, Emile, yeah.
Sir,
Yeah.
isn't it going to be 160 minus the 70?
Yep, exactly that. And why do you know why you do that? So 160 minus the 70, which would give you 90, huh? 90.
Yes, because the 70 states that both people play rugby and cricket. So if you get if you minus the 160 from 70, you get how many people will be in the rugby side only, including the 70.
Perfect, absolutely perfect. Immediately, so basically you have to add up to 160 in total. So that's why you took it away. Thank you so much. And so using Emile's thinking, I think that I can do the same for cricket, and I go 110 minus 70, and that would give me 40 here. but I'm still short of this region on the outside. And so in order to get this, what I need to do is go, well, I know what the total is. It's 220. And so I'm going to go 220 minus 90 minus 70 minus 40. 220. And I'm getting, oh, I agree, Letu, I agree. I get 20 here. Okay, so now that we've solved our Venn diagram, we can start to try and answer the questions. So what is the probability that a randomly chosen boy plays cricket and then does not play cricket and then plays cricket or rugby? So I know this is going to be 220 on the bottom because there's 220 possible people to choose from. The question is, what's the numerator going to be for cricket? It's just going to be 70 plus 40 or 110. Yeah, which is 50% basically, or a half. Let me actually get rid of this thing over here. So that's going to be 50%. What's the probability they do not play cricket? Okay, so Liswa, let me, okay, so did I lose you in the Venn diagram or did I lose you in the probability calculation part?
I'm saying where we had to, for us to get 90. Yes.
90, okay. Do you see that, so when we started, we know that 70 people play both cricket and rugby. So that's this one over here. Now, if we know that 70 play both and 160 play rugby in total, we need to get the 70 up to 160. And so we're adding the 90 to get us up to the 160. Does that kind of make sense? And then we're doing the same with cricket in that we need 110 in total. We know some people play both. So how much do we need to add to 70 to get to 110? We need to add 40. So I'm basically trying to get up to those numbers there. I'm trying to get up to the 110 and the 160. Now, with the probability bits, we say the total is 220. So that's why we're always having that. And then what's the probability they don't play cricket? Well, that's just going to be everything outside of the cricket circle. So it's 90 and 20, which is 110. And again, it's going to be 50%. That makes sense because cricket and not playing cricket are complementary events. So, you know, essentially they're going to add up to 1. What I'm more interested in is what is the probability the person plays cricket or rugby? Lysander, let's unmute you. Yeah. What's your question?
So I wanted to know, so every time you calculate your probability and then you get half, it means that it's 50% every time.
Not every time. In this particular situation, it was 50% because 110 is half of 220. But in this third question, it may not be. The sample space is still 220, right? There's still 220 boys in the question. But how many people play cricket or rugby? Like which regions do you think I'm going to have to count if they play cricket or rugby?
I added, what's this? The intersection plus the rugby and the cricket, and then I got 200.
So I would add the 90 plus the 70 plus the 40. Can you see why? Because it's not and, it's or. So it can be either of the two. It's the union. It's the smiley face one. So this or is smiley face, which means everything that falls within the rugby circle or the cricket circle. So this would be, the probability would be 90 plus 70 plus 40 is 200 out of 220, which is, it's very, very likely you get someone who plays rugby or cricket. If I put it into decimals, it would be 0.9 or 91%. But let me ask you guys another question, which is very close to this. What is the probability that someone plays both, so plays, let's say cricket, and they play rugby? What's the probability that they play cricket and rugby? I want to know based on what we've learned so far today.
Mr. S?
Yes.
Kumritil is asking with the previous question why we don't exclude the 70.
Okay, because OR includes the intersection. So OR can be either the whole of R, it can be an R or C. The intersection is in common. OR doesn't mean you have to choose. It can be either circle and we're happy. So you can either be a rugby player or a cricket player, or you can do both sports. The or does not exclude the middle by definition.
Thanks, Mr. S.
Cool. So what is the probability that someone plays cricket and rugby? Now we're looking for the intersection because you have to play both. You can't just play one of them. The number of possible outcomes are 220, but the favorable outcomes, the ones that count for this question, is 70. And so 70 divided by 220, it's going to be about 32% chance. Now, I want to show you something to sort of get almost towards the end of the lesson here. If we work out, earlier in the lesson, I showed you this identity. So if I said to you, what is the probability of playing cricket or rugby? Cricket or rugby, and we just showed there it was about 32% or 0.32. If we have to work out the probability of playing cricket plus the probability of playing rugby minus the probability of cricket and rugby, what do you think we're going to get? Just based on earlier in the lesson, what identity does that remind you of? So the probability of getting cricket or rugby is 0.32 approximately. I rounded off. If you recognize this from early in the lesson, what do we know this is going to end up being? And you can try this out. Any ideas? Okay, so Rosetta, I agree with you. It's also going to be 0.32 because this is the OR identity or the sum identity. So, and you can try this out for yourself. So, but there isn't going to be time today. But I just want to point out that that identity would be valid in this particular situation. Okay. Are there, and if that still confuses you, don't worry. The main part of today is just about this Venn diagram drawing and working out the probabilities. Are there any more questions, guys and girls, for today? Because I feel like maybe we've done enough for today. We could maybe squeeze in one more if you're feeling okay. So give me a thumbs up if you're feeling okay. Thumbs down if you're feeling a bit. Okay, let's go to Elichle. Hi, Elichle.
Hi, sir. Can you hear me properly?
Loud and clear.
Okay, thank you. I just wanted to ask, whenever you get this question, should you answer in percentages or is it in decimals?
Okay, so it actually depends on the instructions. All of them are equally valid. I would generally leave them in fraction form unless someone asks you to do the percentage. But if you're comparing percentages, if you're comparing probabilities, it's easier to read them in percentages. Does that make sense? It's like, why would you do extra work if you don't have to? But when you're comparing, it's much easier to compare if they're in decimal. would be my answer. Yeah.
Thank you.
Good question though.
Thank you.
Okay. I think then we're gonna call it. I think we're gonna stop there for today because I feel like you guys have understood a lot. If we try and or R. So the probability of C or R is 91. Oh, I might have made a boo-boo here, guys. Sorry, I wrote down the wrong. I was rushing a little bit. And Kumutsila has fantastically pointed out the probability of playing cricket or rugby is 91, not 32. That was the and. So this, and that's why I actually should have worked it out. This is 0.91. And so this would then be 0.91, assuming we're rounding off. Thank you so much, Kumutsile. So I think you can see why I made that error, because I was just, instead of writing the or, I wrote the and one. And it's really important that you see that they are different. It makes sense that the or would be much bigger because the or includes more things. It includes cricket or rugby. And so that should be a much higher percentage than the cricket and rugby, which is less people play both. And so, yeah, watch out for those. That was a boo-boo. Thanks, Owami. Cool. All right, then I'm going to call it unless there's another question, so please do, or if you've spotted anything that you want to query. I actually love that, Kumatsila. I love it that you were paying attention and that a part of being in a classroom is the back and forth. And so please, I do encourage you, if you spot anything like that, let me know straight away. All right, then Lebo, if you could put the poll out to the students, that would be awesome. And then we'll just allow you to do the poll. And then if there are any final questions, I will take those now. Keep those votes coming. It really does help us to understand kind of what is the most helpful pace for most students. Okay.
We really appreciate your feedback, guys.
Yeah, we really do. Especially in a place like this where we don't have as much of your body language as you would in the class. It's a very helpful thing. Yeah, Lusanda, what's your question?
So can you please go back to the previous question? We were talking about older siblings and younger siblings and explain how you got the new data for the new Venn diagram for question.
Okay, so all I did, I'm going to just show you the one region. Do you see the 0.15 here? So
Yes.
when we do Venn diagrams, we can write them as probabilities or as numbers. Now, at the moment, over here, it's written in terms of numbers. To change it to probabilities, all I need is the number of possible outcomes in the diagram. In this diagram, it's really easy because it's 100. So I just went on the outside region, there are 15 people, and I'm dividing it by 100. And so the probability is 0.15. Now, if the number of people in the survey had been 90, I would have had to divide by 90.
Oh, so you only do by the possible outcomes. Oh,
and the same thing for 16. 16 divided by 100 is 0.16. It won't always be that nice, but it's a straight like divide by the number of possible outcomes. Take the number of items you've got, divide by the number of possible outcomes.
Okay, thank you.
Cool. All right, then we're going to close it there for today. Thank